Welcome back, I'm Vida. In this video, I explain one of the key concepts of IEC 70025 measurement uncertainty in a simple and practical way. If you're interested in topics like standardization, calibration labs, or quality management, don't forget to subscribe to the channel and like the video if you find it helpful. What is measurement uncertainty? Every time we perform a measurement, there is always some amount of error or ambiguity that we cannot completely eliminate. This error or ambiguity is called measurement uncertainty. Why do we always have some measurement error? Let's look at a few reasons together. Instrument limitations. No measuring device is perfect and error-free. Every instrument, even the most advanced sensor and laboratory devices, has a specified accuracy range. For example, a precise thermometer may have an error of up to plus minus 0.1 degrees Celsius. This inherent limitation of the instrument causes results to always differ slightly from the actual value. Environmental changes. Environmental conditions such as temperature, humidity, air pressure, and even vibration or electromagnetic noise can affect measurements. For example, when the ambient temperature changes, the performance of sensors may also change, leading to different results. Human performance. Errors caused by the operator are very common. The person performing the measurement might misread the device or record the data incorrectly, or even the way the sample or instrument is placed on the device can change the result. These human factors are an important source of error. Intrinsic sample fluctuations. The sample being measured is not always uniform and constant. For example, in a chemical substance, its composition may vary slightly, or in a metal piece, the temperature at different points may differ slightly. This intrinsic fluctuation in the sample cause measurement results to vary. Measurement methods. The measurement methods or process itself can be a source of error. For example, when there are several different methods for measuring temperature, differences in how each method works or in its timing can cause errors and uncertainty. These factors ensure that no measurement is ever completely accurate, and there is always some degree of uncertainty. That's why calculating and reporting this uncertainty is very important, so we can correctly interpret the test results and trust them. Why is estimating uncertainty important? Accurate estimation of uncertainty helps laboratories ensure the quality of their results, improve the correctness of scientific decisions, and comply with legal requirements and standards. Now we will examine the three main factors that play a role in estimating uncertainty. Reference device or calibrator uncertainty. This factor indicates the level of confidence in the standard or reference device on which other equipment are calibrated. Example, if the reference temperature device used for calibrating the thermometer has low accuracy or error itself, this error will affect the entire calibration results. Measurement process uncertainty includes errors and fluctuation caused by the measurement methods, environmental conditions such as temperature, humidity, and operator skill. Example, a change in ambient temperature while measuring pressure may cause inaccurate results, or an operator who does not properly set up the equipment may introduce errors. Data resolution refers to the limitation of the device in displaying and reading precise results. For example, the number of the digits that can be shown on the device's display. Example, if a device display can only show up to decimal places, smaller differences will not be detectable. How do we combine these factors? According to a standard, the sources of uncertainty are combined using statistical methods such as the root sum of squares to report an overall uncertainty value that represents the acceptable range of results. Now let's take a closer look at how to calculate measurement uncertainty. According to a standard, there are two types of uncertainty sources in uncertainty calculation called Type A and Type B, which are distinguished based on how the data is obtained. A statistical uncertainty Type A. This type is used when data are obtained from repeated experiments or measurements. Examples: repeating the same measurements multiple times with the same device. Calculating the mean and standard deviation of repeated results. A statistical analysis of data, such as ANOVA, standard deviation. This type of uncertainty is used when data can be tested and statistically analyzed. You want to evaluate variation caused by the operator, device, environment, and time. Non-statistical evaluative uncertainty type B, used when data come from non-experimental sources. Examples: information from reference calibration certificates, manufacturer specification of equipment, estimates based on practical experience or published sources. Environmental uncertainties such as temperature or humidity measured by another sensor. This type of uncertainty is used when data are obtained from documented sources, not from direct experiments. Empirical statistical data cannot be generated for that factor. Let's consider a simple example for a temperature sensor. For this, we need to identify and categorize the sources of uncertainty. This table is a simple example of various sources that may cause uncertainty in temperature measurement. The first column lists the sources of error or factor causing uncertainty. The second column specifies the type of these sources, A or B, and the third column provides a brief explanation of each factor. Repeatability of measurement means reading the temperature multiple times with the same sensor and observing the differences. This is type A because it is based on experimental data. Reference device uncertainty means the accuracy of the standard device used to calibrate the sensor. This is type B because it is derived from documentation. Environmental temperature influence means change in the ambient temperature may affect the sensor readings. This is also type B and based on experience or estimation. Display resolution means the limitation in precisely showing numbers on the device, such as the number of the decimal places. This is also type B. Overall, the table tells us that to calculate the total uncertainty, all these sources must be considered, since each can affect measurement accuracy in some way. Now we want to address two concepts, combined uncertainty and expanded uncertainty, and clarify the difference between them. Combined uncertainty. When your measurement is affected by multiple sources of error or uncertainty, each of these sources has a value. Combined uncertainty means merging all these different sources of uncertainty, e.g. type A and type B, into a single overall value representing the total measurement uncertainty. To calculate combined uncertainty, the root sum of squares method is usually used. Square each uncertainty source, sum them up, and then take the square root. Expanded uncertainty. After calculating the combined uncertainty, sometimes it is necessary to increase the uncertainty to achieve a higher confidence interval. Expanded uncertainty is the combined uncertainty multiplied by a coverage factor, usually k equals 2, to represent approximately 95% confidence. This value indicates the range within which the measurement results can be expected with a given level of confidence. In summary, combined uncertainty, the sum of all different sources of uncertainty in a single value. Expanded uncertainty, the combined uncertainty multiplied by a coverage factor to represent a high confidence range, e.g. 95%. What is the coverage factor? When we calculate the combined uncertainty, we get an overall value that shows the amount of error. However, we usually want to be more confident that the actual measured value lies within a certain range. To do this, we multiply the combined uncertainty by a number called the coverage factor to make the confidence interval wider. For example, when the coverage factor k equals 2, we approximately create an interval with a 95% probability that the true value lies within it. If the coverage factor k equals 3, the coverage probability is about 99.7%. Why is the coverage factor important? Because it allows us to numerically specify how confident we are that the measurement results lies within the specified range. If this topic still feels a bit unclear to you, don't worry at all, because I'm going to explain it in simpler terms next. When we say the true value is within the range, it means we cannot measure the exact true value of a quantity, such as temperature, pressure, weight, without error. There is always a small error. That's why instead of saying, for example, temperature is exactly 25 degrees Celsius, we say temperature is 25 plus minus 0.5 degrees Celsius. What does this mean? It means we are not sure that the temperature is exactly 25 degrees Celsius, but we are confident that the true temperature lies within the range of 24.5 to 25.5 degrees Celsius. When we say it lies within this range with 95% probability, it means if you repeat this measurement many times, in 95% of the cases, the true value will fall within this range. Imagine you shot an arrow at a target and say, my aim always has a little error, but 95% of the time my arrow hits the yellow circle. That yellow circle is uncertainty range, and you are saying, I'm confident, 95% sure that my arrow will land in this circle, but I don't know exactly where inside the circle. This is the concept of the coverage factor. How is the coverage factor chosen in a laboratory and on what basis? Main criterion for selection. Confidence level. The coverage factor is directly related to the confidence level that the laboratory wants or is required to report according to customer requirements or standards. If the coverage factor is considered as 1, it corresponds to a confidence level 68%. If it is 2, it corresponds to 95%, and if it is 3, it corresponds to 99%. In standards, the most common value of K is 2. For 95%, unless there are specific reasons to choose a different value. Who determines the value of K? The laboratory determines K according to its documented procedure, taking into account customer requirements, standard or legal, regulatory requirements, policies of the accreditation body, technical and statistical condition of measurement, such as the number of data points or their distribution. Can it be trusted? Yes, provided that it has a clear statistical basis. The confidence level is specified in the calibration report or test result. For example, measurement uncertainty with coverage factor K equal 2 corresponds to an approximate confidence level of 95%. The method for selecting K is defined in the laboratory's procedure, uncertainty evaluation method. Accreditation bodies review during audits to ensure that this selection is documented, reasonable, and consistent with statistical principles. Important note: if the statistical calculations are more complex, for example with low degrees of freedom or uncertain sources, then K must be calculated more precisely using the t-student table and according to the GAM, Guide to the Expression of Uncertainty in Measurement, or EA402 method. Practical example. Suppose a temperature laboratory calibrated a mercury thermometer and reported calibration result 100 degrees Celsius plus minus 0.3 degrees Celsius. K equal to approximate 95% confidence level. The auditor asks, why did you choose coverage factor 2? The laboratory should answer, to determine the combined uncertainty, we identify the sources of uncertainty. Reference uncertainty 0.1 degrees Celsius, repeatability 0.15 degrees Celsius, environmental variation 0.05 degrees Celsius. We combine this value using the root sum of squares method because all sources had a normal distribution and our number of repetition was more than 10. According to the GAM and EA402 guidelines, we can use a coverage factor of K equal to for 95% confidence. Let's summarize what we've discussed with a simple numerical example and calculate the uncertainty for calibrating a temperature sensor, thermistor or RTD. The goal is to determine the combined uncertainty and finally report the expanded uncertainty using a coverage factor. Example: calibration of a temperature sensor at 25 degrees Celsius. Suppose you calibrated a temperature sensor in the laboratory and obtained the following result. Measure value 25 degrees Celsius. Now we want to calculate the overall uncertainty of this value. First, according to the table, we identify the factors that contribute to the calculation of uncertainty. Then we square all the standard deviation values, sum them up, and take the square root of the total to calculate the combined uncertainty. Now for the final report with a coverage factor of k equal 2, for 95% confidence we calculate the expanded uncertainty. Final calibration report. Measure temperature value 25 degrees Celsius plus minus 0.23 degrees Celsius with coverage factor k equal to approximate confidence level 95%. Note that the lower the uncertainty, the more accurate and reliable the measurement results are. This is crucial for laboratories and industries. Imagine a pharmaceutical manufacturing plant where a temperature measuring device has high uncertainty. This can lead to incorrect temperature readings and affect product quality. Such a problem may result in product recalls or legal penalties, which can be very costly. So it is better to review some strategies to reduce measurement uncertainty. Use more accurate and calibrated equipment. Devices with higher precision and regular calibration reduce measurement errors. Control environmental conditions. Managing temperature, humidity, and other environmental factors during measurements reduces their impact on results. Operator training and experience. Skilled and experienced users minimize human errors. Perform repeated measurements. Repeatability. Repeating measurements and analyzing results helps identify and reduce random errors. Use standardized and precise methods. Applying verified and documented measurement protocols reduces process-related errors. Regular maintenance and servicing of equipment. Routine maintenance prevents sudden errors from occurring. Use noise and interference reduction tools, for example, filters or protective devices against electromagnetic noise and vibrations. By following these steps, measurement uncertainty can be reduced, resulting in more accurate and reliable results. Thank you for staying with me until the end of this video. By subscribing, liking, and commenting, you give me the motivation to create better and more useful videos. In the upcoming videos, we will discuss other practical concepts. If you have any specific topics related to this subject, I would be happy if you share them with me in the comments.